All right, how was that? Yeah, so and then I have another guitar in my closet that I don't really play anymore. I play that one because that's my favorite guitar. That's because I was born in '99, so it's as old as I am. It's been on the planet Earth 26 years, just as long as I have. So it's kind of been through the same things as me. So that's why I like it. Then it's so I wanted to get one of those my birth year guitar. And so, but I do have a PRS 245 SE, just a the round body, not like the not the kind of like the Gibson body. That one's pretty smooth to play. I just need to put some new strings on it, but I'm just too lazy to. Hey Diego, how's it going, my guy? Welcome in, friend. Awesome to hear from you. How you doing, dude? Any of you guys play guitar out there? We're just showing off the guitar. Okay, let's go ahead and get into the stream. Let's go ahead and grab my keyboard is just charging. Let me go and grab it. All right. Sweet. Doing fine. Hey, thanks for the follow, Diego, on Twitch. Cheers to you, mate. 5 big pumps. Boom, boom, boom. All right, thanks, Diego. I appreciate you, man. Hey, you were number 180, man. Congrats. Follower goal reached. Thanks, you. Look at that. Hey, Newt. How's it going? I'm studying Java right now. Sweet, dude. How's that been? Okay, let's go ahead and get into today's lecture. So I'm going to start. Pardon me, guys. Let me go ahead and ping the Discord. Say, starting lecture. All right. If you guys aren't in the Discord, you should join the Discord. All my resources are in there for free. Let's give a quick little intro. Hello, everybody. My name is Michael. I'm 26 years old. I got a degree in 2021, at the end of 2021, in human biology and a minor in chemistry. I was more heavily focused on the chemistry side of things, though, so I probably should have just majored in chemistry. But it kind of how it worked out, I guess. Kind of went hand in hand with the courses I needed to take. But I work as a formulation chemist for a biotech company. I'm a scientist too, kind of a mid-level, kind of approaching kind of a senior level scientist soon, hopefully. Well, I guess. And I've been, I specialize in kind of manufacturing kind of bulk level formulation. More specifically, kind of like balancing, analyte matrices by hand to produce a theoretical yield and then actually perform those balancings and formulations within the lab as well. So think of it just like advanced cooking, putting a bunch of stuff together to make an end product. Yeah. Anyways, I have been teaching myself how to code for about a year now, a little over a year. I've been streaming every single day for about 8 or 9 months now, and it's been a lot of fun. We've been teaching ourselves pretty heavily a lot of things. We've been moving quite quickly. So we've taken courses like Harvard CS50P, Harvard CS50X. We've read books like Python Crash Course. We've read a lot of DSA in Python. We've read some of Fluent Python. We've read some other things here and there. And now we're getting into this course here. So I'm going to go ahead and start my recording so I can go ahead and intro this course, because I am doing a follow along series on the channel, so you guys can go back and watch these like with a friend, I think that's a lot more entertaining to watch them alongside someone else. Kind of hasn't gained the traction I thought it would, but I think it might be like a slow burn. I honestly, I think it's a really good idea. Like I've never seen anyone else do this, like do like pair lecture watchings. So that's what kind of was like my idea is if people are watching the lectures, wouldn't they rather watch it with like someone else to kind of break up the monotony of it and kind of, if you're like watching it kind of with a streamer or like, or a watch back or something, I feel like it kind of would help. Also, you're watching them take notes while you're taking notes, so in case you miss anything or you can get a second perspective, or I think it could really be a great like learning resources to watch someone else watching the lecture basically, because you might be able to get all the insights from that learner's perspective as well. Um, but yeah, so let's go ahead and start this thing here. So, all right, hello everybody. We are back doing Introduction to Computational Thinking in Data Science, which is the MIT Open Courseware. This is 6002, Lecture 2. We are going to be diving on in today. Let's go ahead and get started here. So let me pull up the videos. Lecture 2, Optimization Problems is the lecture we're going to be watching today. If you guys haven't watched Lecture 1, it's already up on my channel. And then if you guys are wanting to watch this live with me on stream, we are streaming right now, so say hello to the chat. Cool. So catch me streaming every single day around 7 p.m. PST to do courses like this with me, solve problems, build projects, and a lot more. Cool. Let's go ahead and pull up our notes. MIT's Trick 6000. Okay, that was our lecture 1 notes. Let's go here and make a lecture 2. Look at us, guys. We are staying consistent. Right? Optimization problems. Cool. All right. Are we ready, everybody? Let's go ahead and get started into Lecture 2 of MIT 6000, Introduction to Computational Thinking in Data Science, Lecture 2, Optimization Problems with John Guttag. All right. Let's go ahead and get into this.
The following content is provided under a creative...
All right, let's turn up the volume here. Let me know how the volume is, you guys. You guys will be my testers. There we go. All right, let's get into this.
Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of
Hit that
MIT
sub
courses,
button if you're here, guys.
visit MIT OpenCourseware at
I'll hit it with a like.
ocw.mit.edu.
All right, let's get into this.
We ended the last lecture looking
John.
at greedy algorithms.
Greedy algorithms.
And so
with
today I
John.
want to discuss the pros and cons of greedy. Oh, I should mention,
Okay.
in response to popular demand, I have put the PowerPoint up. So if you download the zip file, you'll find
The PowerPoint wasn't
the
even up.
questions, including question 1, the first question,
This guy is dated.
plus the code, plus the PowerPoint.
This is only 2016.
We actually do read Piazza and sometimes at least pay attention.
At least I have
We should pay
Piazza.
attention all the
Did you guys
time.
ever use your Piazza
All right.
back in class?
So-
I never used that thing.
What are the pros and cons of greedy? The pro, and
right.
it's a big pro, is that it's really easy to implement.
Okay, let's just really quickly here. So pros, we'll say the pros and cons of greedy. Right, so we have right, so we have one pro, or we have Come on, Mike. Pros. 1. Easy to implement. 2 is computationally efficient. Okay, and then got some cons here. But does not always yield the best solution. Right? And we'll say you don't even know how good the approximation is. You don't even know how good the approximation is. Cool. Let's keep going here.
To implement, as you could see. Also enormously important, it's really fast. We looked at the complexity last time. It was n log n, quite quick. The downside, and this can be either a big problem or not a big problem, is that it doesn't actually solve the problem, in the sense that we've asked ourselves to optimize something, and we get a solution that may or may not be optimal.
Mm-hmm.
Worse,
Makes sense.
we don't even know in this case how close to optimal it is. Maybe it's almost optimal, but maybe it's really far away. And that's a big problem with many greedy algorithms. There are some very sophisticated greedy algorithms we won't be looking at that give you a bound on how good the approximation is. But most of them don't do that. Last time, we looked at an alternative to a greedy algorithm that was guaranteed to find the right solution. That was a brute force algorithm.
Right? Yeah.
The basic idea is simple, that you enumerate all possible combinations of items, remove the combination whose total units exceed the allowable weight, and then choose the winner from those that are remaining.
Yeah.
Now let's talk about how to implement it. And the way I want to implement it is using something called a search tree. There are lots of different ways to implement it. In the second half of today's lecture, you'll see why I happen to choose this particular approach.
Okay.
So what is a search tree? A tree is basically a kind of graph, and we'll hear much more about graphs next week. But this is a simple form where you have a root, and then children of the root. In this particular form, a search tree trees you have 2 children.
Okay.
So we start with the root.
Just like a basic tree, okay.
And then we look at our list of elements to be considered that we might take. And we look at the first element in that list. And then we draw a left branch, which shows the consequence of choosing to take that element, and a right branch, which shows the consequences of not taking that element.
Okay.
And then we consider the second
and you
element.
do it again, whether you take the second one or
so
third.
on and so forth, until we get to the bottom of the tree.
Okay.
So by convention, the left element will mean we took it. The right direction will mean we didn't take it. And then we apply it recursively to the non-leaf children. The leaf means we get to the end. We've considered the last element to be considered, nothing else to think about. So when we get to the code, we'll see that in addition to the description being recursive, it's convenient to write the code that way too. And then finally, we'll choose the node that has the highest value that meets our constraints. So let's look at an example. So my example is I have my backpack that can hold a certain number of calories, if you will. And I'm choosing between, to keep it small, a beer, a pizza, and a burger.
Okay.
3 essential food groups. So the first thing I explore on the left is take the beer.
Take the beer.
And then I have the pizza and the burger to consider. I then say, all right, let's take the pizza. Now I have just the burger. Now I taste the burger. So this traversal, or this generation of the tree, is called leftmost depth most. So I go all the way down to the bottom of the tree. I then back up a level and say, all right, I'm now at the bottom. Let's go back and see what happens if I make the other choice at the one level up the tree. So I went up and said, well, now let's see what happens if I make a different decision, as in we didn't take the burger. And then I work my way, this is called backtracking, up another level. I now say, suppose I didn't take the piece of pizza. Now I have the beer only and only the burger to think about, so on and so forth, until I've generated the whole tree. You'll notice it will always be the case that the leftmost leaf of this tree
It's empty.
has got all of the possible items in it, and the rightmost leaf none.
Yeah, the
And then
rightmost
I
is right.
just check which of these leaves meets the constraint. And what are the values? And if I compute the value and the calories in each one, and if our constraint was 750 calories, then I get to choose the winner, which is, I guess it's the pizza and the burger. Is that right? The most value under 750. Okay. All right. So that's the way I go through, and I do that. It's quite a straightforward algorithm. And I don't know why we draw our trees with the root at the top and the leaves at the bottom. My only conjecture is computer scientists don't spend enough time outdoors.
They like that
All right.
one.
So now let's think of the
All right.
computational complexity of this process. Well, the time is going to be based on the total number of nodes we generate. So if we know the number of nodes that are in the tree, we then know the complexity of the algorithm, the asymptotic complexity. Well, how many levels do we have in the tree? Just the
N
number of
items.
items, right?
Yes, and
Because
items.
at each level of the tree, we're deciding to take or not take an item. And so we can only do that for the number of items we have. So if we go back, for example, and we look at the tree, not that tree, and we count the number of levels, it's going to be based upon the total number of items. We know that because if you look at, say, the leftmost node at the bottom, we've made 3 separate decisions. So here it's counting the root,
Left
it's 1,
first,
2,
depth
it's
first,
n plus
enumeration.
1. But we don't care about plus 1, right? When we're doing asymptotic complexity. All right, so that tells us how many levels we have in the tree. The next question we need to ask is, how many nodes are there at each level? And you can sort of look at this and see the deeper we go, the more nodes we have at each level, right? In fact, if we come here, we can see that the number of nodes at level I, depth I of the tree, is 2 to the I.
So computational complexity, right? So the time based on number of nodes generated, right? The time is based on number of nodes generated, right? Or in other words, the number of items in the list or decisions or decisions made or something, right? Number of levels is the number of items to choose from. Oh no, it's total number of nodes generated. Right, so then the number of levels, height, would it be depth? whatever, number of levels is the number of items to choose from, right? N. And then the number of nodes at level I is 2 to the power of I. Right? Because you can either make a yes or no decision per every number of I down to that depth. You have to recursively, or exponentially account for all the decisions made for I in the previous depths, right? So I want to talk about this really quick. Getting some titles. How do my notes look for search trees? Can we talk about the time based on number of nodes Is this just decisions made? You know, it's a very solid, so clear understanding how a search tree works, especially in the context of decision problems like optimization, backtracking, or brute force enumeration. Let's dig into your question about time-based on number of nodes generated. You're right, on the right track thinking in terms of decisions. Key concept, time equals work equals nodes explored. When we talk about time complexity for a search tree, we're often referring to the number of nodes generated or explored in the tree. Each node corresponds to a state or a decision point in the recursive process. So yes, the time is proportional to the number of decisions made across all paths in the tree. Tree structure recap. Given n items, and for each item you make 2 decisions, include or exclude. If this creates a binary decision tree, height or depth of the tree equals to n. Each level doubles in size, right, leaving 2 to the power of n nodes. The total time complexity is O to 2 to the power of n. The total number of nodes, and therefore total recursive calls or decisions made, is 2 to the power of I, which equals, for every I up to n, which is 2 to the power of n plus 1, 2 to the power of n plus 1 minus 1, I think, for what, the root? Which simplifies to the O of n squared for big O purposes. So if your algorithm visits all of these nodes, node pruning, the worst case time complexity is exponential. What's the number generated? Oh, because you have to do it for all possible cases, right? It's not just one linear case. So what does the number generated means? When your notes say time is based on a number of notes generated, that's correct. Each note represents a unique state, a subset of decisions made so far, a function call in the recursive solution, and a unit of work for your CPU to compute. So yes, in a brute force decision tree, time equals total decisions, which equals to total nodes. Bonus, pruning equals n efficiency. In smarter algorithms like branch and bound and whatever, we don't need to worry about that. Okay, so let's say then, okay, that makes sense. We are exploring an exhaustive optimization or something to find all possible solutions, then pick and choose our favorite, right? That for just a linear time would only be one single path, but we are in a nutshell, search trees like a brute force or backtracking, you're exploring all possible combinations or paths. Each node equals a partial decision. Time grows exponentially because you're trying every possibility. It's the exhaustive part. You generate the entire solution space, then pick the best. Subset sum, knapsack, or choose some from many problem, right? Linear time algorithms are like greedy or straightforward loops. You're not branching, you're just following one path through the data. Time grows proportionally. Scan a list of max values or do a greedy pass through the sorted items. Yeah, right. You're trading off speed for thoroughness. Interesting. No interest in games? You mean no interest in Fortnite? I think I said that in the Discord. I play games. I just had to prioritize other things, right? I had to grow up a little bit for a little bit. I had to kind of, I'm still grinding away, but I've gotten to a point where, you know, you don't want to, you don't want to give up too many things that you find to give you passion, and it's okay to, play, things like video games and stuff if it gives you, a relief from and a stress, like when I play video games, I really don't think about anything else besides the game. So it helps to kind of really take my mind off things so I can really kind of just let it all go and then come back refreshed. Because when I'm playing the game, I'm just focusing solely on the game and nothing, it really does take, so I really understand why people do play. I personally just, stopped playing for a little while because I wanted to grow this channel and grind my CS skills. And now that I've kind of gotten a little bit of foundation under me, so now I can kind of learn a bit quicker and I don't have to like not really grind as hard. I'm still grinding hard, but like it's not as exhaustive as it was before. I'm a little bit more used to it now. I feel like I have a little bit more bandwidth to maybe start playing some games every now and then. It's kind of like a reward too for my efforts here as well. So I was a huge gamer as a kid, man. I brought my DS, my Nintendo DS, and my Game Boy Advance, my SP, with me everywhere I went, growing up. And I have more hours in Pokemon Fire Red and Leaf Fire Red than probably anything I've ever done in my life. I grinded Pokemon up to level 100 by hand, just raw grinding because I was that passionate about building my squad up. No rare candies, no nothing. Okay, this is good. Let's keep going here. All right, I'm gonna make a little thing in the time frame so I know to cut right here. All right.
That makes sense. If you remember last time we looked at binary numbers and we're saying we're representing our choices as either 0 or 1 for what we take. If we have n items to choose from, then the number of possible choices is 2 to the n, the size of the power set. And so that will tell us the number of nodes at each level. So if there are n items, the number of nodes in the tree is going to be the sum from 0 to n of 2 to the I, because we have that many levels. And if you've studied a little math, you know that's exactly 2 to the n plus 1. Or if you do what I do, you look it up in Wikipedia, and you know it's 2 to the n plus 1. Now, there's an obvious optimization, right? We don't need to explore the whole tree. If we get to a point where the backpack is overstuffed, there's no point in saying, should we take this next item, because we know we can't. Right? I generated a bunch of leaves that were useless because the weight was too high. So you could always abort early and saying, oh, no point in generating the rest of this part of the tree because we know everything in it will be too heavy.
Yeah.
Adding something cannot reduce the weight. It's a nice optimization. It's one you'll see we actually do in the code, but it really doesn't change the complexity, right? It's not going to change the worst cost complexity. All right, so exponential, as we saw, I think in Eric's lecture, is a big number. We don't usually like 2 to the n. Does this mean that brute force is never useful? Well, let's give it a try. We'll look at some code. Here's the implementation.
Okay. So max value to consider is equal to...
So it's max val of to consider and avail. And then we say if to consider is empty or avail is
0.
0. Avail is an index. We're going to go through the list using that to tell us whether or not we still have an element to consider. Then the result will be the tuple 0 and the empty tuple. Okay? We couldn't take anything. This is the base of our recursion, right? Either there's nothing left to consider or there's no available weight. The avail is the amount of weight is 0 or to consider is empty, all right? Well, if neither of those are true, then we ask whether to consider sub 0, the first element to look at, is dot cost is greater than availability. If it is, we don't need to explore the left branch, right? Because it means we can't afford to put that thing in the backpack, the knapsack. There's just no room for it. So we'll explore the right branch only. Here's the implementation.
Okay, so this says if to consider is equal to an empty list or available is equal to 0, return result 0 with a empty tuple inside it, right? A tuple with a 0 as one value and an empty tuple as another value. Elif, right, to consider index of 0, get the cost is greater than available, right? Well, I'll say the result is equal to max value, which is a call to this function again, on consider of 1 forward, right, and available. Else, we'll say next item is to consider index 0, right, which is going to pull the next item with val plus equals to the next item get value. Okay, gotcha.
The empty tuple, recursion, right? Well, if consider cost is greater than availability, if it is, we don't need to explore the left branch, right? Because it means we can't afford to put that thing in the backpack, the knapsack. There's just no room for it. So we'll explore the right branch only. And so the result will be whatever the maximum value is of to consider of the remainder of the list with the first element sliced off, and availability unchanged. All right, so it's a recursive implementation saying now we only have to consider the right branch of the tree because we knew we couldn't take this element. It just weighed too much or cost too much or was too fattening in my case. All right. Otherwise, well, we now have to consider both branches. So we'll set next item to consider of 0, the first one, and explore the left branch. Now on this branch, there are 2 possibilities to think about, which I'm calling with val and with to take. So I'm going to call max val of to consider of everything except the current element.
Yeah.
And pass in an available weight of avail minus whatever, well, let me widen this so we can see the whole code. It's not going to let me widen this window anymore. Shame on it. Let's see what happens if I get rid of the console. All right, well, we'll have to do this instead.
So the available cost, right?
We're going to call max val with everything except the current element and give it avail minus the cost of that next item of to consider sub 0, okay? Because we know that the available weight has to have that cost subtracted from it.
Mm-hmm.
And then we'll add to with val next item dot get value. So that's the value if we do take it. Then we'll explore the right branch. What happens if we don't take it? and then we'll choose the better branch. So it's a pretty simple recursive algorithm. We just we go all the way to the bottom and make the right choice at the bottom and then percolate back up, like so many recursive algorithms. All right, and then we have a simple program to test it. I better start a console now if I'm going to run it. And then we'll test maxval. So I'm building the same thing we did in Monday's lecture, the same menu. And I'll run the same test greedies we looked at last time.
Okay.
And we'll see whether or not we get something better when we run the truly optimal one. Well, indeed we do. You remember that last time, and fortunately this time too, the best we did was a value of 318. But now we see we can actually get to 353 if we use the truly optimal algorithm. So we see it ran pretty quickly and actually gave us a better answer than we got from the greedy algorithm. And it's often the case, and if I have time at the end, I'll show you an optimization program you might want to run, that it works perfectly fine to use this kind of brute force algorithm on. All right, let's go back to the PowerPoint. So I'm just going through the code again that we just ran.
Okay.
This was the header we saw.
So max value, we have to consider and available. Assumes to consider a list of items and available a weight. Returns a tuple of the total value of a solution to O1 knapsack problem and the items of that solution.
Consider as the items.
To consider those items that the nodes higher up. To consider those items that the node higher up in the tree corresponding to earlier calls and recursive calls that could not be considered.
It corresponds to nodes higher up the tree and avail, as I said, the amount of space. And again, here's what the body of the code looked like.
So if the items that are still to be considered are empty, there's no more left, and or the available space is 0, we're going to return this base case. Okay? Elif, the item that we're going to consider, the first item we're going to consider, the units is greater than the available space, we're just going to return a call of, we're going to say result equals to this, and then we're going to return a call to that. But you get hit by if this with val here on that too, so. So there is no with val in this case, so it will just return result here. So max value to consider is the rest of the string of the list of items forward and the available weight, right? Else the next item is equal to consider 0, right? The one we're going to consider. We're going to say the max val call to consider 1 through, and the available is the next item, the units, right? Minus from available. So we're going to make the recursive call to the next item and to the reduced available space. Once we get this call back to us, right, if it reaches a base case, we're going to add the value to the next item, get value, right? And then we're going to create this tuple here, right? Okay, yeah.
I took out the comments. One of the things you might think about in your head when you look at this code is putting the comments back in. I always find that for me, a really good way to understand code that I didn't write is to try and comment it. And that helps me sort of force myself to think about what is it really doing. So you'll have both versions. You'll have the PowerPoint version without the comments and the actual code with the comments. And you can think about looking at this and then looking at the real code and making sure that your understanding jives. All right. Should point out that this doesn't actually build the search tree, right? We've got this local variable result starting here that records the best solution found so far, right? So it's not the picture I drew where I generate all the nodes and then I inspect them. I just keep track. As I generate a node, I say, how good is this? Is it better than the best I found so far? If so, it becomes the new best. And I can do that because every node I generate is, in some sense, a legal solution to the problem. Not probably, rarely is it the final optimal solution, but it's at least a legal solution. And so if it's better than something we saw before, we can make it the new best. This is very common, and this is, in fact, what most people do when they use a search tree, is they don't actually build the tree in the pictorial way we've looked at it, but play some trick like this of just keeping track of their results. All right, any questions about this? All right. We did just try it on the example from lecture 1, and we saw that it worked great. It gave us a better answer. It finished quickly. But we should not take too much solace from the fact that it finished quickly, because 2 to the 8th is actually a pretty tiny number. Almost any algorithm is fine on working on something this small. Let's look now at what happens if we have a bigger menu.
Okay.
So here's some code to do a bigger menu. Since, as you will discover if you haven't already, I'm a pretty lazy person, I didn't want to write out a menu with 100 items or even 50 items. So I wrote some code to generate the menus.
With random, okay.
And I used randomness to do that. This is a Python library we'll be using a lot for the rest of the semester.
Yeah, that's really easy.
It's used for any time you want to generate things at random and do many other things, and we'll come back to it a lot. Here we're just going to use a very small part of it.
Yeah.
So to build a large menu of some num items, we're going to give the maximum value and the maximum cost for each item.
Yeah.
We'll assume the minimum is, in this case, 1. Items will start empty, and then for I in the range number of items, I'm going to call this function random.randint.
And this is pretty easy. I kind of want to skip forward, but I'll
That
stay for you
takes a
guys.
range of integers from 1 to, actually, in this case, max val minus 1. Or 1 to max val, actually, in this case. And it just chooses one of them at random. So when you run this, you don't know what it's going to get, right? Random.randint might return 1, it might return 23, it might return 54. The only thing you know is it will be an integer. And then I'm going to build menus ranging from 5 items to 60 items. Build large menu, the number of items with the minimum value with a max val of 90 and a max cost of 250.
Why didn't you do a
Pleasure in
range
calories.
function?
And then I'm going to
Bruh, why didn't he just do a range? He did it up here. Why list all this out? Just do a range with a skip.
test max val on each of these menus. All right? So building menus of various sizes at random, and then just trying to find the optimal value for each of them. All right,
That was
let's
a
look at the
brutal,
code.
that one was really easy.
It is, well, let's comment this out. So we don't need to run that again.
No hotkeys. Got to use the. Dang.
So build a large menu, and then we'll try it for a bunch of items and see what we get.
Dang. Brutal. No hotkey on that. Edit. Comment.
So it's going along, trying to menu with up to 30 went pretty quickly. So that's even 2 to the 30 didn't take too long. But you might notice it's kind of bogging down. We got 35. And I guess I could ask the question now. It was one of the questions I was going to ask as a poll, but maybe I won't bother, is how much patience do we have? When do you think we'll run out of patience and quit? Well, if you're out of patience, raise your hand. Well, some of you are way more patient than I am. So
I don't even know what that is, Tim.
All right. We were trying to do 40. It might have finished 40.
They were using
45.
Morse.
I've never waited long enough to get to 45. It just is too long. So
No,
that raises
dude.
the question, is it hopeless?
Logic, you unbox gloves? Come on, man. Where's our luck? We're 0 for 10. I'm gonna make a spreadsheet or something and maybe write a little Python script to I think it'd be fun for us to write a little Python script to track the number of items we get. To track the cases.
And in theory, yes. As I mentioned last time, it is an inherently exponential problem. The answer is in practice, no, because of something called dynamic programming, which was invented by a fellow at, I think, the RAND Corporation called Richard Bellman, a rather remarkable mathematician / computer scientist.
Imagine coming up with something like that.
He wrote a whole book on it, but I'm not sure why, because it's not that complicated.
Roasted.
So
His whole life work just roasted.
when we talk about dynamic programming, it's kind of a funny story, at least to me. I learned it, and I didn't know anything about the history of it, and I was trying to, and I had all sorts of theories about why it was called dynamic programming. You know, how it is, how people try and fit a theory to data. And then I read a history book about it, and this was Bellman's own description of why he called it dynamic programming. And it turned out, as you can see, he basically chose a word because a description that didn't mean anything. Because he was doing mathematics, and at the time, he was being funded by a part of the Defense Department that didn't approve of mathematics, and he wanted to conceal that fact. And indeed, at the time, the head of defense appropriations in the US Congress didn't much like mathematics.
Why?
And he was afraid that he didn't want to have to go and testify and tell people he was doing math. So he just invented something that no one would know what it meant. And years of students spent time later trying to figure out what it actually did mean.
Yet here we are.
Anyway,
Everybody
what's
wants
the basic idea?
to program.
To understand it, I want to temporarily abandon the knapsack problem and look at a much simpler problem, Fibonacci numbers.
We've seen this one
So
before.
you've seen this already with cute little bunnies, I think, when you saw it.
Let's go ahead and just get that here, and then we'll do a note here and say recursive implementation. You can also spell this Fibonnaci. Right. So let's go. I think we can go like this, right? Can we go Python? Can we write code like this? Def. Or is it just pi? No. How do you do it? Anyone know how to do the Python and Markdown? Is it triple? I don't know. Triple tick pi? And then a triple tick. And do I put this in here? Oh, there you go. Clutch. Clutch, Adele. Clutch. Alright, we'll def fib here of n, right? We'll say if n equal to 0 or n equal to 1, else return fib of n less than 1 plus fib n less than 2. Clutch. Okay, let's keep going.
N equals 0, n equals 1, return 1. Otherwise, fib of n minus 1 plus fib of n minus 2. And as I think you saw when you first saw it, takes a long time to run. Fib of 120, for example, is a very big number. It's shocking how quickly Fibonacci grows. So let's think about implementing it. If we run Fibonacci,
The previous
maybe
two
we'll
numbers
just do that.
summed together. Okay.
So here's fib of n, and let's just try running it. And again, we'll test people's patience. And we'll see how long we're letting it running. I'm going to try for I in the range 121. We'll print fib of I.
Okay, so if you have like 10 here, n equals 10, it doesn't equal 0 or 1, so we're going to call fib on 9 and plus fib on 8. That goes fib on. So then 1 finally gets returned back to here, plus another. Obviously, you get hit with what? A 1 right here as well. So you get. I'm curious. I never actually have really done this. Let me take this really quickly into fib.py. Let me paste this here. Let me call fib on 10, and then let me print fib of 10, right? So then let me go here and call this and run the debugger here. Okay, so we'll step into this. N equals to 10, so it's going to skip that. It's going to open up a call stack for right? Five and 1. So n equals 9 now, which we called here. Eight, 7, 6, 5, 3, 2. We're opening up the call stack all the way down to 1. Now we return 1 back to here. N is now, because n is 2, so because that was the last call stack that didn't reach the base case, right? So n is 2 in this now on this refold, and then this is filled in as a value of 1, and so we're going to call this to the base case. Now n goes to 0, so now we have 1 plus 1. On the n equals 2. Yeah, return fib equals 2. Now on the n equals 1, return It's going pretty fast. Let's do like a smaller number. Let's do like 3. Okay, so it goes 3, 2, 1, returns 1 to the n equals 2 call stack. The n, that hits here. Now we have 0 here. That returns back to the n equals 2 call stack. Now we're at the n equals 3. Because we have a current fib is 2. Oh, I print fib of 4. Or sorry. Just 5. I call n of 120. Do I get the same number he's getting? It's taking forever. So let's go here. Let's say, can you walk me through the recursive call stack of a problem or a function like this? And let's say like 10 or like this is a classic recursive definition of a Fibonacci sequence, but shifted. Fib 0 equals 1, fib 1 equals 1. Instead of the usual 0, 1, 1, 2, 3. Okay, so let's step by step call stack for fib 5. Let's trace it top down, what you see when you're calling, then bottom up, see how it resolves. So fib 5 calls fib 4 and fib 3. Fib 4 calls fib 3 and fib 2. Fib 2 calls fib 1 and fib 0. Fib 1 here calls fib 1, okay. So then you just sum these values together. 1, 2, 3, 8. So let's imagine the function call stack where each call waits for the child return. So fib5 calls fib5, calls fib4 and fib3, waits for fib4, which waits for fib3, which waits for fib2, which returns 1, 1. This guy returns 2. Okay, interesting.
Comes clomping along. And it slows down pretty quickly. And if you look at it, it's kind of surprising it's this slow, because these numbers aren't that big, right? These are not enormous numbers, right? Fib of 35 is not a huge number, yet it took a long time to compute. So yeah, the numbers are growing pretty quickly, but the computation actually seems to be growing faster than the results, right? We're 37. You know, it's going to get slower and slower, even though our numbers are not that big. So the question is, what's going on? Why is it taking so long for Fibonacci to compute these results? Well, let's kill it. And look at the question. And to do that, I want to look at the call tree.
Okay.
So this is for Fibonacci of 6, which is only 13, which I think we would most of us agree is not a very big number.
No.
And let's look what's going on here.
Okay. So fib of 6
If you look
calls
at
fib
this,
of 5, 4.
what in some sense seems really stupid about it?
We're doing repeated work
What is it
across
doing
multiple same
that
numbers.
a rational person would sort of not want to do if they could avoid it?
We're already calling fib of 4, fib of 3, fib of 2, fib of 1 elsewhere earlier in the code for some of these leaves or later
It's bad
depths.
enough to do something once, but to do the same thing over and over again is really wasteful. And if we look at this, we'll see, for example, that fib 4 is being computed here, and fib 4 is being computed here. Fib 3 is being computed here, and here, and here. And do you think we'll get a different answer for fib 3 in one place than we get it in the other place? You sure hope not, right? And so you think, well, what should we do about this?
We need to cache stuff.
How would we go about avoiding doing the same work over and over again? And there's kind of an obvious answer, and that answer is at the heart of dynamic programming. What's the answer? Yeah. Exactly. And I'm really happy that someone in the front row answered the question, because I can throw it that far.
You
store the answer, and then look it up when you need it. Because we know that we can look things up very quickly, right? A dictionary, despite what Eric said in his lecture, almost all the time works in constant time if you make it big enough, and it usually is in Python. We'll see later in the term how to do that trick. But so you store it, and then you'd never have to compute it again. And that's the basic trick behind dynamic programming, and it's something called memoization.
Memoization, that's what it's called.
As in, you create a memo and you store it in the memo. All right, so we see this here. Notice that what we're doing is...
So trade a time for space, right? So we'll say trade time for space. Create a table to record what work we have already computed. In Fibonacci, before computing fib of x, right? Check if the value of fib of x is already stored in the table. If so, take value from the table instead of computing, right? If not, compute it and then add it. See. Storing storing the results of previously done work to avoid repeating work. Let's see if it likes that definition here. Your notes on memoization are excellent, concise, and accurate. Memoization is a process of processing of caching the results of expensive function calls so we don't repeat the same computation multiple times. It's a classic example of trading time for space. You can use extra memory or a dictionary or array to store previous computed values. In the case of a Fibonacci, this means before computing fib of x, check if it's already in the memo table. If it is, return the stored value. No need to recurse. If not, compute it recursively and store it in the table for future use. Memoization prevents overlapping subproblems. The very thing that makes naive recursion slow in problems like Fibonacci, subset sum, knapsack, grid traversal, edit distance, Catalan numbers. Okay.
Is trading time for space. It takes some space to store the old results, but negligible relative to the related to the time we save. All right? So here's the trick. We're going to create a table to record what we've done, and then before computing fib of x, we'll check if the value has already been computed. If so, we just look it up and return it. Otherwise, we'll compute it. It's the first time, and store it in the table. So here's a fast implementation of Fibonacci that does that. It looks like the old one, except it's got an extra argument, memo, which is a dictionary. The first time we call it, the memo will be empty. So it tries to return the value in the memo. If it's not there, an exception will get raised. We know that. And it will branch to here. If it's empty.
Okay, so let's quickly jot this down. So def fast fib. Let's do fib.py, fast fib.py. Okay, so we're taking the same number. Now we have a memo that we're going to be passing in, right, through the recursion, tracking all of our computations downward, right? Um, Joanne, this fixes your problem here, right? This the function in the note says assumes n is greater than 0 or equal to 0. So if n is equal to 0 or n is equal to 1, we're going to return 1. So as we decrement this number down, n, once we hit a base case of either 0 or 1, we return a value of 1 to the recursive call. Right? Or 2, or just return, right? So we're going to try and return memo index n. Oh, interesting. So they're going to try to catch the key error and then handle that instead of checking if in memo, right? They're using Python here to try and then catch the exception as like an if, pretty much, right? Except if you get a key error, right, which is basically handling the if statement for checking if in memo, right? We're going to set result equal to fast fib call, recursive call on n less than 1 and the memo. Plus, right, fast fib on n less than 2 and the memo. Okay, then we're going to add the results into the memo, right? So memo of this number is equal to the result that we computed. And then we're going to return the results here. I'll say check if the current n is in the memo as a key. If Python raises a key error or detecting no matching key, perform the computation and save the result into the memo. If Python finds a matching key for n and in memo, return the pre-computed result of fast fib of n. Nice. Well, I can't go ahead and change the MIT slides, dude. What do you want me to do? What do you want me to do? Go into my monitor and want me to email what is his name? Greg? I can't remember. What's his name? John. Want me to email John and tell him? Yeah, exactly. That's what I was referring to. You want me to email him and tell him to put
return the value in the memo.
I'm just copying their code
for the notes. If it's not there, an exception will get raised. We know that. And it will branch to here, compute the result, and then store it in the memo and return it. So it's the same old recursive thing we did before, but with the memo. Notice, by the way, that I'm using exceptions not as an error handling mechanism, really.
Yeah, Tim, you
but
email
just as a flow of control. To me, this is cleaner than writing code that says, if this is in the keys, then do this, otherwise do that.
He's talking about the
It's
exceptions.
slightly fewer lines of code, and for me at least, easier to read, to use try except for this sort of thing.
Yeah.
All right, let's see what happens if we run this one. So we'll get rid of the slow fib.
Tim stepping up to the plate.
And we'll run fast fib.
Email MIT. He might have retired by now, probably. Tell him Joanne sent you.
Wow. We're already done with fib 120.
Yeah, Professor John for sure retired,
Pretty
chilling
amazing,
right now.
considering last
He's
time we
cashing
had
out his
stuff around
Nvidia
40,
stock and he's chilling. Come on.
right? It really works, this memoization trick. You know, an enormous difference.
I wonder when they figured that out. It was like such a light bulb moment for them. Like, oh my god, no way.
When can you use it, right? It's not that memoization is a magic bullet that will solve all problems. You need the problems it can solve, or can help with, really, is the right thing. And by the way, as we'll see, it finds an optimal solution, not an approximation, is when problems have two things called optimal substructure and overlapping subproblems. So what do these mean? We have optimal substructure when a globally optimal solution can be found by...
Okay, so we have when does it work? When to use memoization. Right? We'll say optimal substructure. Right? And then we have overlapping subproblems. 1 and 2. So optimal structure says, let me just move this up for you guys. A globally optimal solution can be found by combining optimal solutions to local subproblems, right? Okay, and then in overlap, okay, so we'll have an example here. Right? Say, we'll put some Python code here. For x greater than 1, globally optimal solutions can be found by combining optimal solutions to local subproblems. A globally optimal solution can be found by combining optimal solutions to local subproblems. Anybody have some better wording for this, maybe? Like, can it better, like, explain optimal substructure a little bit better? For x greater than 1, fib x equals to fib of x less than 1 plus fib x less than 2. Adele, bruh. Come on, man. Come on, man. Come on, Adele. Come on, man. Adele says, oh, by the way, Michael, have you heard of MIT Open Courseware? It's a great website for finding courses. I use it for math, but I'm sure you can find CS in there. Adele, you better be sarcastic right now. You better be sarcastic. You better be sarcastic right now. Killing me. Y'all killing me in these chats sometimes. Oh, you guys are funny. Mike fell for the rage bait. Clip it. Clip farming, baby. Clip farm. Streamer problem, streamer. All right, here we go. We're almost done. 14 more minutes. Let's keep going. Okay, hold on. Overlapping subproblems, right? So finding an optimal solution involves solving the same problems multiple times, right? And we'll say example, compute fib x multiple times. Right down. You're good. You're funny, my guy. You're funny.
By combining
I appreciate the laugh.
optimal solutions to local
Okay,
effects.
so
We have optimal substructure when a globally optimal solution can be found by combining optimal solutions to local subproblems. So for example, when x is greater than 1, we can solve fib x by solving fib x minus 1 and fib x minus 2 and adding those two things together. All right, so there's optimal substructure. You solve these two smaller problems independently of each other and then combine the solutions in a fast way. All right? You also have to have something called overlapping subproblems. This is why the memo worked, right? Finding an optimal solution has to involve solving the same problem multiple times. Even if you have optimal substructure, if you don't see the same problem more than once, creating a memo, well, it'll work. You can still create the memo. You'll just never find anything in it when you look things up, because you're solving each problem once. Okay?
okay.
So you have to be solving the same problem multiple times, and you have to be able to solve it by combining solutions to smaller problems. Now, we've seen things with optimal substructure before, right? In some sense, right, what merge sort worked that way, right? We were combining separate problems. Did merge sort have overlapping subproblems?
Not really.
No, right? Because, well, I guess it might have if the list had the same element many, many times. But we would expect mostly not, right?
Yeah.
Because each time we're solving a different problem because we have different lists that we're now sorting and merging. So has half of it but not the other. So dynamic programming will not help us for sorting, cannot be used to improve merge sort. Oh well. Nothing is a silver bullet. All right, what about the knapsack problem?
What about it?
Does it have these two properties?
Okay, so let's say, what about the O1 knapsack problem?
So we can look at it in terms of these pictures. And it's pretty clear that it does have optimal substructure, right? Because we're taking the left branch and the right branch and choosing the winner. But what about overlapping subproblems? Are we ever solving, in this case, the same problem at 2 nodes?
Would you just compile into a set?
Well, do any of these nodes look identical?
Yeah, sometimes you have a couple pizzas.
Well, in this case, no.
No, not in this case, actually.
So we could write a dynamic programming solution to the knapsack problem, and we will, and run it on this example, and we get the right answer, we would get 0 speed up. Because at each node, if you can see, the problems are different. We have different things in the knapsack or different things to consider. Never do we have the same contents and the same things left to decide. So maybe it was not a bad answer if that was the answer you gave to this question.
I like this guy a lot.
Let's look at a different menu. Okay. So this menu happens to have 2 beers in it. Now, if we look at what happens, do we see 2 nodes that are solving the same problem?
Yeah.
The answer is what? Yes or no?
Yeah, you have 1 beer and 1 in the knapsack.
I haven't drawn the whole tree here. Well, you'll notice the answer is yes. This node and this node are solving the same problem. Why is it? Well, in this node, we took this beer and still had this one to consider. But in this node, we took that beer. But it doesn't matter which beer we took. We still have a beer in the knapsack and a burger and a slice to consider.
Yeah.
So we got there different ways by choosing different beers, but we're in the same place. So in fact, we actually, in this case, do have the same problem to solve more than once. Now, here I had 2 things that were the same. That's not really necessary. Here's another very small example. And the point I want to make here is shown by this. So here I've again drawn a search tree. And I'm showing you this because, in fact, it's exactly this tree that we'll be producing in our dynamic programming solution to the knapsack problem. Each node in the tree starts with what you've taken, initially nothing, the empty set.
Yep.
What's left, the total value in the remaining calories. There's some redundancy here, by the way. If I know what I've taken, I could always compute the value and what's left, but this is just so it's easier to see. And I've numbered the nodes here in the order in which they get generated. Now, the thing that I want you to notice is when we ask whether we're solving the same problem, we don't actually care what we've taken.
Okay.
We don't even care about the value. All we care is
the remaining calories,
how much room we have left in the knapsack, and which items we have left to consider. Because what I take next, or what I take remaining, really has nothing to do with how much value I already have, because I'm trying to maximize the value that's left, independent of previous things done, right?
So
Similarly, I don't
the same
care
number of items left
why
for
I
all
have
other options.
100 calories left. Whether I used it up on beers or burger doesn't matter. All that matters is is that I just have 100 left.
Okay.
And so we see in a large, complicated problem, it could easily be in a situation where different choices of what to take and what to not take would leave you in a situation where you have the same number of remaining calories. And therefore, you're solving a problem you've already solved. At each node, we're just given the remaining weight, maximize the value by choosing among the remaining items. That's all that matters.
Yeah.
And so indeed, you will have overlapping subproblems, as we see in this tree for the example we just saw. The box is around a place where we're actually solving the same problem, even though we've made different decisions about what to take, A versus B, and in fact, we have different amounts of value in the knapsack, 6 versus 7. What matters is we still have C and D to consider, and we have 2 units left.
Mm-hmm. So no matter which one you take, like, it's solving the same problem.
All right, it's a small and easy step, and I'm not going to walk you through the code because it's kind of boring to do so, of how do you modify the max val we looked at before to use a memo. First, you have to add the third argument, which is initially going to be set to the empty dictionary. The key of the memo will be a tuple. The items left to be considered and the available weight.
Yeah.
Because the items left to be considered are
Those were
in a list,
memorize. Okay.
we can represent the items left to be considered by
A length?
how long the list is.
Yeah.
Because we'll start at the front item and just work our way to the end.
Because the order of the items stays constant
And then
when
the
they were
function
taken out. Okay.
works essentially exactly the same way fastfib worked. I'm not going to run it for you because we're running out of time. You might want to run it yourself because it is kind of fun to see how really fast it is. But more interestingly, we can look at this table. This column is what we would get with the original recursive implementation, where we didn't use a memo, and it was therefore 2 to the length of items. And as you can see, it gets really big, or as we say at the end, huge.
Yeah.
But the number of calls grows incredibly slowly for the dynamic programming solution. Right? In the beginning, it's worse. Oh well. But by the time we get to the last number I wrote,
Boss.
we're looking at 43,000 versus some really big number I don't know how to pronounce.
Oh, yes.
18
Number of
somethings.
calls.
So incredible improvement in performance. And then at the end, you know, it's a number we couldn't fit on the slide, even in tiny font, and yet only 703,000 calls.
Interesting.
How can this be? We know the problem is inherently exponential. Have we overturned the laws of the universe? Is dynamic programming a miracle in the liturgical sense? No.
Liturgical?
But the thing I want you to carry away is that computational complexity can be a very subtle notion. The running time of fast max val is governed by the number of distinct pairs that we might be able to use as keys in the memo to consider and available. Well, the number of possible values of to consider is small, right?
Okay,
it's bounded by the length of the items.
Yes.
If I have 100 items, it's 0, 1,
Up
2,
to 100.
up to 100. The possible values of available weight is harder to characterize, but it's bounded by the number of distinct sums of weights you can get, right? If I start with 750 calories left, what are the possibilities? Well, in fact, in this case, maybe we can say only 750 because we're using with units. So it's small, but it's actually smaller than that because it has to do with the combinations of ways I can add up the units I have. All right, I know this is complicated. It's not worth my going through the details in the lectures. It's covered in considerable detail in the assigned reading. All right, quickly summarizing lectures 1 and 2, here's what I want you to take away.
Assigned reading.
Many problems of practical importance can be formulated as optimization problems.
Okay.
Greedy algorithms often provide an adequate, though often not optimal solution.
Yeah, okay.
Even though finding an optimal solution is in theory exponentially hard, dynamic programming really often yields great results. It always gives you a correct result, and it sometimes, in fact, most of the times, it gives it to you very quickly. Finally, in the PowerPoint, you'll find an interesting optimization problem having to do with whether or not you should roll over problem set grades into a quiz. And it's simply a question of solving this optimization problem.
Should we give that one a go next time? Nice! Woo! All right, if you guys are here, I appreciate you guys being here and joining me for this lecture. This was the MIT Lecture 2 Optimization Problems for the MIT Introduction to Computational Thinking and Data Science course, which is the 6.0002 course, 6.0002. It is the second semester of kind of their more kind of bridging the gap from kind of that beginner Python, like, just basics, to actually getting into more, computational thinking, programming, dynamism, more advanced types of ways to actually go about using Python and things like that, which is exactly kind of the gap that we're trying to bridge here and our move forward through DSA, through building projects and lots of other things, which is really awesome. Cool. So that was lecture 2, optimization problems. Sweet. You guys know that you guys can access my notes here that I'm taking throughout the course if you want to get them yourselves for the example codes that I'm writing here and my notes, my personal notes here. You guys can access them on my GitHub. I'm tracking them, and I actually pushed them up recently to a repo, so they are live. So you can check them out. And I'm doing a course weekly, a lecture follow along series. Also on this channel, but more of a breakdown in depth in my Discord, link down below, completely for free. All of my content is for free regarding programming and everything for my resources and what I've done so far to learn. So if you are interested in following a similar route of building projects that like I have done and learning concepts similar to myself, not that I'm doing anything right, I'm just trying my best to just do this in any way possible. So yeah, I appreciate you guys being here and hanging out with me for this week 2 lecture. This was awesome. So let's go ahead and add up here. Let's say finish lecture 2. And let's push that up. Boom. Nice. So lecture 2 is finished. Let me know what you guys think so far about the course. This was actually a really nice lecture. I've actually never had a formal lecture on dynamic programming. It was kind of with this thing I heard in the background people talk about. I learned about memoization just picking up through some LeetCode problems, but never actually gave like a formal definition of anything. And so this really actually helped to kind of put this to words and actually provide some more clarity on what this actually is and how to use it more efficiently and actually understand when to use it in the appropriate time. So like when you have overlapping subproblems and optimal substructure, like of solving smaller and smaller problems to solve the overarching larger problem at hand, within. So these two kind of conditions, when met, you can use dynamic programming or memoization rather, a feature of dynamic programming, I believe, to solve some of these problems, which is interesting and cool. I really like that. Gonna definitely, so tomorrow we're going to get into lecture 3. So the assignments here, we have up until problem set 1 in the syllabus isn't due until lecture 4, right? So at the end of lecture 3, I would say lecture 4 is the start of problem set 2. So we're gonna watch lecture 3 tomorrow, and then we'll do problem set 1. So I'm gonna follow the course guidelines here. We'll watch this theoretic models lecture tomorrow, and then probably either after the lecture or the next day work on the problem set 1 assignment here, space cows transportation zip right here, and so we'll get into that as well, which will be cool. And then we also have some readings here. I don't have the book by at MIT Press. Oh, it's John's book. Wow, John's really making you buy his own book? John, Tough, dude. He's plugging his John's plugging his own book to the students. He's making. Is that what professors usually do? I never really like bought books like in terms of like not a lot of my stuff was required for books. It was a lot of more of just lecture and professor work. So is that what like these comp sci professors do? Is they write books and then they have all the students go fund their book during their class? All right, we'll stop the recording there. W hustle, yeah. John's hustling. He's hustling. Do we respect the hustle or do we? That was a 50-minute lecture, but that took us an hour and 50 minutes. Dang, brutal. But I feel like if we took no pauses, I wouldn't have gotten as much out of that. I needed the pauses to really kind of understand and ask questions. So it is what it is. Yeah, we'll have to look up a copy online or something. I'm sure there's a copy online. We'll throw it in the Discord. Yeah, we'll have to do some leak code ones too. So yeah, this is a good point too. We'll practice a couple of memoization problems on leak code once we kind of get through the problem set one here as well. Yeah. All right, you guys. Let me see here. Should I try one? Um, Let me go here. Let's see here. Problems. Recursion. Here's the Fibonacci question. So what I'll do is we'll do this one tomorrow so I can take some time to step away and then come back and solve this again because we solved this today. Um, it's only three Fibonacci or three memoization problems that are labeled easy. We've already solved one of them. The Fibonacci sequence T of n is defined as follows. T sub 0 equals 0. T sub n plus 3 for all n greater than 0. So the T of n plus 3 is equal to T of n, T of n plus 1, T of n plus 2 for all n greater than or equal to 0. 25 over T. I don't really know what does this mean here. T of n plus 3 for all n's greater than or equal to 0. So if the It's just all of the previous numbers combined, summed, no? Plus the current call. Um, it's kind of scummy to be honest. He's already made hella bank, and I guarantee you he's in Aruba right now. Aruba W. He's in Aruba with Boston right now, Tim. With the Celtics. He's on the beach with them. Michael, I found a PDF version of the book. One is from 2013, one is from 2021. Yo, yeah. Send on Discord. Adele, clutch, hearts for Adele. Coming through with some couple copies here. So for this leak code problem, is this saying that for every value of n, it's just the previous, all the Fibonacci sequence, it's just all previous values summed together up to n minus 1? Is that what this means? Yeah, thank you guys so much for being here. We got 34 people here on YouTube right now, 30 people here. So huge, huge dub stream right now. A lot of people. So if you guys are here, sub up. We're at 2669. Can we get to 2670? Who's here not subbed? If you guys are, I appreciate you guys stream every single day, teaching myself how to code. We're doing various courses here. We're doing MIT's 6.0002 course, Introduction to Computational Thinking and Data Science, which is really awesome. So like if you're here, leave a thumbs up. Let's get 30 likes on the stream. It really helps to keep pushing our content out. I'm working hard for you guys, keeping new things out, posting videos too. Python crash course, try it yourself problem walkthroughs, all that jazz, like re-uploads of the stream. So I'm working, I'm grinding out here. I'm tired of this, Grandpa. Okay, so like Fibonacci, but previous 3 instead of previous 2. Oh, okay. Okay. So should we try this one? These are pretty similar then to the other ones. So should we try these tomorrow to get some more practice? I mean, we could try it here. So let's just say, okay, so our base case right here, right? So if n, right, if the value of n is less than 0, we're going to return 0, right? Or this would be invalid, right? So return like what, none? Or return, I don't even know what we would return. You assume, right? Are we just assuming? So if n is equal to 0, we return 0. If elif n equal to 1, we return just 1. And if n is equal to 2, we return 1. Right, we return 1. Okay. So we would make a call here, right? For JavaScript, my PC took 8.6 from 45. Oh, nice. If n is equal to 0, return 0. If n is equal to 1 or 2, return 1. Okay? So now we're going to recursively call but let's memo this, right? So let's say, so do I need another function here? So I'll say helper, def helper, pass in n and memo, right? So if I say, and we'll establish memo out front, to be equal to just an empty dictionary. So I'll say if, so else, right, if n in memo, we're going to say result is equal to, or we're just going to return memo key of n, right? If it's not in memo, then we're going to say the result is equal to helper on n less than 1 memo plus helper n minus 2 passing in the memo plus helper n minus 3 passing in the memo. Okay. Then we say memo index of n equals to the result, and then do we return result here? So now do we call help return helper on n in the memo? Typo. Oh, no way. Let's go! Yo, let's go. First try. We learned, we were paying attention in the lecture, y'all. We were paying attention. Come on. I'm like glue. Call me Elmer. Come on. Nice. Thanks for the support, Dragon. Let's go. All right, that was good. Now, see, that was a good solidification. Now, memoization, like that's awesome. That really helps. I should put some like LeetCode problem links per chapter to help out with some of the stuff. Maybe I might throw that in as well. Yeah, let's try it. Let's try to sketch a tree diagram, and then we'll hop off after that. Yeah. So let's go. Oh, wait the bird. Okay, so let's say you have, right, the only case that we can do this on without reaching a base case is fib of 3, right? So we would have try fib of 3, right, which calls 3 separate things, right? So try fib of 3 calls this. It calls here, here, and here. It calls try fib of 2, try fib of 1, and try fib of 0. Okay? These hit a base case, right? This example is pretty easy, but these hit a base case of 0, 1, and 1. We sum those up, get 2 back here, right? So is there test results on fib of 3? What about a fib of 4? Or fib of 3? So now let's try a TF of 4, right? So a TF, a triple Fibonacci of 4, which we'll call triple Fibonacci of 3, which we'll call triple Fibonacci of 2, which we'll call triple Fibonacci of 1, right? This is a base case. So this is done, right? We'll say done. And the result that we're going to return here is equal to 1. This is also a base case, so we're done here, and the result that we're going to return here to be summed is equal to 1. Now on this guy, we're going to do what we did before. So we open up a try tree here for the 3 recursive calls that we're going to do for TF of 2, TF of 1, and try Fibonacci of 0. Oh, we've already computed this guy. Already done for these guys, right? So we're going to go into our memo for but we haven't computed this guy yet, which is a base case, right? So this one's done. So the res here that's returned is equal to 0. So we've already returned these. So this will be 1 plus 1 plus 1. So right, fib of 3, try fib of 3 gives us a result of 1 plus 1. And then we have plus try fib of 2 plus try fib of 1, our base cases, which equates down to 1 plus 1 plus 1 plus 1, which equals to 4 for try fib of 4. Right. Let's go. All right, y'all. Sweet. Are we feeling good, better about memoization and dynamic programming now? How are we feeling in chat after today's lecture? I'm feeling really good about that one. I'm gonna be honest. That really helped me just to break down every minute of recursion I get exposure to. Really, just keep soaking it in. Just keep soaking it in until I'm completely soaked. Pause. But because recursion is something, I don't know, it's something I definitely struggle with more than other concepts I've learned so far. It's definitely probably the hardest programming concept I've had to teach myself so far. I thought time complexity and everything was even more easier because that was more math, but just understanding the call stack and what's going on and the return, that's what's really tricky about recursion. And so it's definitely probably the most difficult thing I've had to learn. And then I'd say even more difficult so than object-oriented programming, in my opinion. I don't know why. It's just I do struggle with recursion. I'm being transparent with you guys. It is one of my not my stronger suits on these LeetCode problems. I spent hours just struggling through some of these ones. Cool. If you guys are here, leave a like for today's stream. It was awesome stream. We got gaming coming up on this channel, so we got we did a test stream where we opened up 10 cases. We were 0 for 10. We opened up 10 cases this weekend, but we'll be back and doing some more. Probably, I'm pretty busy on Thursday and Friday. I actually have work off. I released all my product on Wednesday, so right now I'm really busy at work. This past week, I've had a couple of days where I didn't stream this past week because I'm super busy at work. I'm right at the end of my product where I build this entire formulation process, which computes to like millions of dollars of revenue for the company. It's that expensive. of materials. It's biological based. It's really expensive stuff with extreme markup on margins, and like it's really expensive. So it is a lot of stress and pressure to make sure it's right and it has good quality, and I'm not having errors or issues for my product, which really hurts my career negatively. So I'm really in the grind focusing on this. I'm done with the product. I've released over half of it. There's 6 portions of the product total. I've released 4 of them, so I have 2 more, which are going back-to-back days, tomorrow and Wednesday. So the July 22nd, July 23rd, and then I'm done with the product for this go around. And it's going to be a really successful go around, in my opinion. A very nice quality product for them, so they're going to be really happy with that, in my opinion. And so as a result, I've had to work a couple of weekends. Like on this yesterday, I did work. I had to go in and do some work. Last weekend, I had to go in and do some work. So they are providing me as a salary employee, to keep morale up. They are providing me with a couple of comp days, which is really nice. For having to do those extra hours and skip lunches and really just grind to really get this out the door. And so I do have Thursday and Friday off, boys. So we are going to be doing a stream then. I'll probably do a good long stream, probably like a good 6 hours or so. That's my goal. I want to have a nice, good long stream those days, and possibly also do some gaming stream those days too. Let me know what you guys think. I'm sorry for yapping on here, but I am considering putting the gaming streams behind the lowest fee I can do, membership channel fee, like of 99 cents a month. The coding and content and everyday streams will be completely free on the channel. Nothing will change, but in order to kind of break up we lost a sub, someone didn't like that idea. Tim, it's all your fault. I am considering doing that just to help kind of break apart the more not professional but more like serious stream with like of coding and stuff with help break apart the more casual, more personal, like and also the gaming might be more like an adult kind of stream where like it's more late night, and people on Counter-Strike say some pretty wild stuff, so I don't know. So yeah, anyways, let me know what you guys think about that, and yeah, it's just a thought I had. Yeah, like that's what exactly, like this channel isn't family friendly. I don't say that word because that word can doom you in the streaming world, I've heard, but I keep it just kind of professional, right? I keep it professional, keep it chill, and and obviously so like all parties and everyone can really have a good time. But when you play CS and Counter Strike, the rage, let me tell you, it comes out. So I was thinking about just making a 99 cent, just as low as I can get. So if you guys are interested in watching those streams, and there will be quite a bit of them, I will try to make it worth it for you guys, But let me know what you guys think. All right, you guys. So today was a very successful stream. We solved this leak code problem first try after taking a watch of getting some practice with optimization problems with MIT here in 6.0002. Introduction to Computational Thinking and Data Science from fall 2016. This is lecture 2. We're going to watch lecture 3 tomorrow, and then we'll work on problem set 1 after that. So make sure you guys are back here tomorrow for the lecture. If you guys missed this one, I'm going to be re-uploading it to the channel, but you can also just go back and watch the VOD that's on the channel for today and watch it there as well. But if you want a condensed version, just wait a couple of days and I'll have it uploaded to the channel, just like I did for lecture number 1. And then we went ahead and solved this leak code problem, which is further solidified. Which we saw an example of Fibonacci in this lecture. Dynamic programming, memoization, and so we put that to the test, and we're able to actually solve this one first try, which is really awesome. I'm really proud of that. So we were actually paying attention and learned from this lecture. Awesome. So let me know what you guys think about that. You guys can access the notes on Discord, on GitHub and Discord. And then in my Discord as well, right, I have a 6.0002 MIT course section here that you can access, kind of like a roadmap of my entire learning journey so far. I'm gonna go ahead and make updates for each week as I go about it, each lecture, providing information along each and some resources for each lecture and my notes and everything. So I did the same thing for Harvard CS50X. So let me know what you guys think about that. Yeah, see, you guys can see all of my posts here for week 0 all the way through week 9. And then some other people have made some posts too. So feel free to contribute your learning into the Discord as well. It's a great place to be. It's completely for free. It's great, awesome. All right, you guys. Thank you guys so much for being here. I'll be back tomorrow. Dun, dun, dun. Well, we'll continue on with MIT here. It's really awesome. I'm really enjoying this course so far. It's a lot of fun. Professor John is a really great guy. And so I'll see you guys tomorrow. Please leave a like and subscribe if you're new. The likes really, truly, they do help the stream. YouTube really, really like sees those likes as like a factor of your engagement. So hit it with a like, and I'll see you guys later. Thank you guys so much for hanging out with me tonight, and message me on Discord if you have any questions, and I'll see you tomorrow. Have a good one. I feel bad for leaving 31 people here, but it is what it is. Bye, guys.